Yesterday all of you got the LED blinking program. It is working for all of you. Any problems are there? That LED blinking. Everybody was able to do, no? So next you write a program for this circuit. So here when you are pressing this button, this is a push button. When you are pressing this button, this LED should be on. When you are releasing it, it should be off. That is switch with the LED program. So for that, first you make this pin as RC0 as input, RB0 as output. Then test this bit whether it is 1 or 0. If it is 1, then switch on the LED. If it is 0, switch off the LED. So there is no need of that delay program and all. Delay program is not required. So write the program for this. So this is your program. Type this first. So here in the first statement I had made TRISB as output in this statement. Second statement BSF TRISC, 0. That means what? BSF TRISC, 0. BSF TRISC, 0. By this you are setting RC0 as input. BSF TRISC, 0 means I am setting RC0 as input. Then for initializing I am clearing the port B, that is I am switching off the LED. Then in this loop what I am doing is I am checking BTFSC port C, 0. So whenever you are writing a program for testing certain bit, you test the opposite condition. For example, here I need to test whether the switch is, when switch is pressed, 1 will be coming. So I need to test whether this bit is 1. So if you want to test this bit whether it is 1, you give the just opposite condition, BTFSC. If you want to test it for 1, you give the you check the other condition, that is bit test file register skip if clear. So if it is clear, then what you should do? If this bit is clear, what you should do? If this bit is clear, then what you should do? If it is set, what you should do? Switch on this LED. So if it is clear, switch off the LED. So that is done here. If it is clear, so here I am checking the condition whether it is clear. If it is clear, then go to L1 will be skipped. So if it is clear, what you should do? LED should be off. That is given by this BCF port B, 0. BCF means that bit RB0 will be made as 0. That is that LED will be off. And the other condition, that is if it is set. If it is set, then what it will do? If it is set, then go to L1. That is, if it is set means opposite condition of this. Then this statement will be executed. Go to L1. L1 is BSF port B, 0. Go to loop. BSF means LED is on. Then again why you are checking for this BTFSC port C, 0. Second time why I am testing. Second time why I need to test. If I am omitting this statement, there will be one problem. That is, if this condition is true, BTFSC that is this bit is 0, control will come here, that is that LED will be off, again that LED will be on. First it will be off, if this statement is not there, again it will be on. So it will be generating one blinking LED. So in order to avoid that, again I am checking for this clear. If it is clear, skip this, go to loop. If it is set, BS of baud B comma 0, that is LED will be on, and this will be infinitely going on executing. Go to loop. So is there any doubt in this program? We will draw the circuit. Listen here. So first we need to have a push button. So for searching push button, you again go to this component mode, pick from library, there search for button. Search for button. For getting push button, you search for button. Then double click on this button. So you can see button active, SPST push button. What is meant by this SPST? What is meant by SPST? What is this type of switch? What is this? SPST. What is the full form SPST? Single pole, single through, through or throw, anyone you can tell. So what is meant by pole in this? What is pole, what is through? What is pole, what is through? So this thing is known as your pole. This is your pole. So in a switch we can see one movable contact will be there. That is known as pole. And throw means this is the throw. So here you are having only single pole and single throw. That is SPST. Here, what is the name of this? Single pole, double throw. SPDT. Here, double pole, double throw. DPDT. Double pole, double throw. This is not for throw. Because for one switch you can have only two contacts. And when you are moving one switch, automatically the other one will also move. It is like this. When you are moving one contact, automatically the other contact will also move. So here you are taking push button, so search for button. Then you need to have that pull down resistor, 1K. For taking this, you search for MINRES 1K. MINRES 1K. MINRES 1K. Then you take the first one. MINRES 1K, take the first one. And double click on that. So you can see your button as well as your resistor has been added to your devices. Next you need to draw the diagram. So first you take the resistor, keep it somewhere here. Then you can rotate also. Right click on that component, rotate. Then you can take that switch, keep it somewhere here. Then here we need to have power and ground, no? You need to have power as well as ground. So that will also, that you can take it from terminals mode. Here one button is there, no, terminals mode. From there you can get power. Click on this power, you can get that arrow mark, power. That is default VCC. Power means it is the default power of the controller, that is VCC, 5 volt. Then you take the ground. After that, wire all these things. From RC0, connect to all these things. So here you can see when it is running, the switch is open, no? When the switch is open, due to this pull down resistor, you can see all these are zeros. But in the Proteus, if you are omitting this resistor also, it will work. In this Proteus, there is some problem for the simulation. All simulation may not be correct. In this Proteus, you try removing this. Then also it will work sometimes. But when you are doing actual hardware, this resistor should be there, otherwise you will not get the output. So in the Proteus, if you are removing this, then also it will work. But in actual hardware, you need to have that. And there is one speciality for this port B. There is one speciality for port B. If you are using port B as input, if you are configuring port B as input, that port B is having internal weak pull up. For this port B, that port B peripheral itself is having internal weak pull up resistors. So there is no need of this pull up resistor. This is pull down resistor if you are doing the other configuration. If you are connecting in the reverse manner, that means you are connecting the switch to ground. So if you are connecting like this, you need to have a pull up, no, usually. But if you are using port B, there is no need of connecting this external pull up, because internally all the pins are pulled up. There is a weak internal pull up inside port B. So whenever you are trying to connect one switch, you try to connect it in the port B. So whenever you are going to connect a switch, you try to connect it in the port B. So this pull up resistor can be avoided, because port B is having weak internal pull up. It does not have weak internal pull down, it is having only weak internal pull up. At this moment I need to move the position of the resistor. For example, I need to move the LED little rightwards. So what you should do? Or at this moment you need to add one more component. So how we will add? So for adding component as well as moving the component, again you should go and click the component mode, because it was like this. Here you had selected only terminals mode. So whenever you want to change some component or move component, you need to again go and click on this component mode. Then only you can make any changes in the circuit. Next peripheral we will see USART. Why are you using this USART? Any idea? Why do you use this USART terminal? Any ideas, sir? Or what is meant by USART? Full form? Full form of USART? Universal Synchronous Asynchronous Receiver Transmitter. What are the different type of communication you are seeing basically? Parallel communication and serial communication. So what is the basic difference between these two, parallel and serial? What is the difference? Parallel means, for example, you are having 8-bit parallel transmission. So there 8-bit will be simultaneously transmitted. But then what is meant by serial? For example, I need to do this 8-bit transmission in serial. How we will do? Bit by bit you will be transmitting, one after another. So what is the disadvantage of using parallel port? Which one will be faster, parallel or serial? But there is a disadvantage for parallel port. What is the disadvantage? Because more lines are required. No? In parallel communication, more lines are required. If we are having a 16-bit parallel transmission, then 16 lines are required. That is one of the disadvantages. But speed is high for parallel. But when you are going for serial transmission, only 2 lines are required, transmit and receive. So complexity reduces. But speed will get reduced, for some little speed will be reduced. But circuit will be less complex. That is why we are going for serial transmission. And in serial transmission also it is divided into certain types. One is USART. Second one, I2C. Have you heard about I2C? I2C SPI. There are so many other protocols, I2C, SPI, CAN, etc. All this comes under the category serial transmission. So one of that simplest serial transmission is USART. So I told 2 lines are required. So this is the pin diagram of your PIC, and these 2 lines, 26 and 25, these are the lines used for serial transmission. So here you can see RX, that is receive, TX, that is transmit, and here you can see most of the pins are having multiple functionality, right? No, here this pin can be configured either as digital IO pin, that is port C is 6th pin. RC6 means port C is 6th pin, that is it can be configured as digital IO. It can also be configured as TX pin. TX means it is a pin that is used for USART. So here you can see CK means it is some other functionality. So in this pin itself you can see there are 3 functionalities. Why they had given multiple functionality for so many pins? Is there any reason? They would have given separate functionality. No? Why they had given multiple? But no, in order to reduce the pins, only that much. If they want to give separate function for separate pins, pin number will go on increasing. So whenever you are adding few peripherals, pin number will also increase. So when number of pins are increasing, cost will increase, cost of production will increase, power will increase, complexity also increases. So that is why they had multiplexed the functionality for most of the pins. So here these 2 are the pins which is utilized for USART, that is transmit and receive. Then why are you using this? For example, USART, why do you use? For example, I need to communicate between your controller and my system or your desktop PC. For that it can be used. Have you seen the serial port at the back of the CPU? This is that port, this pin. This connector is known as Db9 connector. this connector is known as Db9 connector. This is male, this is female. So through this connector you will be doing the serial transmission. So for example, I need to communicate between your controller and your PC. In that case, you will use serial transmission and connection will be given through this pin. And here you can see there are 9 pins. Out of that you will be using only 3 pins, 2, 3 and ground, that is 5. That is 2, 3 and 5 only will be used by us. 2 means receive, 3 means transmit, 5 means ground. Right, no? You can see here 2 receive, 3 transmit, 5 ground. Only these 3 pins are required for basic serial communication. So from the PIC, transmit will be connected to receive of this, that is 2. So that we will see here. So this is your PIC, this is your PC, and from the PIC, transmit pin will be connected to receive of PC. From the PC, transmit pin will be connected to receive of PIC. Ground will be common. Why do you need to ground 2 circuits? Why are you connecting this? Because whenever you are trying to interface between 2 circuits, these 2 circuits should have same reference or same ground. Your PC is one circuit, your controller is having some other circuit, and both of it is having different power supply. So definitely the ground will be different. So in order to make these 2 grounds common, these pins should be shorted. So this is the minimum connection. And there is one more problem. Your PIC is working on TTL logic, no? It is working on TTL logic. That is, logic 1 means 5 volt. Logic 0 means 0 volt. But your PC's serial transmission standard is known as RS-232 standard. In the PC, the standard used for serial communication is RS-232. In PIC, standard used for serial communication is TTL. So in RS-232, logic 1 means it is a range of voltage, that is -3 to -15 volt. Logic 0 means +3 to +15 volt. So in the case of RS-232 communication, there is a range of voltage for logic 1 and logic 0. But here you are having only 5 and 0. Then how can you interface, how will you send some data? Because these 2 are working on different logics, different standards. So we cannot interface. It is same as 2 people speaking 2 languages. They cannot understand anything. So we need to have somebody to translate this in between these 2 persons, right? Some translator should be there. So similarly, you are having a level converter. So this is also one IC known as MAX232. So this is known as a level converter. So what it will do? It can convert TTL to RS-232. Similarly, RS-232 back to TTL. Both the level conversion it can do. So here TX is connected to transmit in of MAX232. From the transmit out, you are giving into TX of PC. Similarly, you are giving the receive also. So this IC will take care of the conversion between these 2. That is standard conversion or level conversion. That is 5 volt, it is getting converted to this range. 0 volt, it is getting converted to this range. So they can communicate between these 2. So this is the basic connection. And other than PC, there are so many other modules which is having serial interface. For example, wireless transceivers, RF transmitter, have you seen? RF small transmitters. In toy cars their transmitter is there, no? Wireless. All that is working basically on serial transmission. And Zigbee module, have you seen Zigbee? That is also one wireless transceiver module. So Zigbee, Bluetooth, Wi-Fi, so many things are there. All these things can be interfaced through this USART. So other than PC, you can interface these peripherals also. So whenever you are interfacing those peripherals, there is no need of MAX232, because all the peripherals such as wireless transceiver, Bluetooth, Wi-Fi, all these things works on TTL logic, so no need of this. But when you are interfacing with your PC, this is required because it is working on RS232. Any doubts in this? So this is your connection. Then how will you configure this USART? I told for configuring all the peripherals there are certain special function registers associated with it. So these are the registers associated with the serial transmission. These are the registers, these are the bits. And here you can see, some of the bits are in white color, all the others are in grey color. So whichever bits that is in white color will be used for configuring this, because so many bits are there, all the bits need not be used. So I will show the steps for programming this with the less number of bits. So these are the registers, ind con. This one first, this ind con register now we will not be using. This is used for configuring the interrupt, that is configuring interrupt of USART. Now we will not be seeing that, but all these registers we will see. PIR1 means peripheral interrupt register. PIR means peripheral interrupt register 1. RCSTA means receive status register. TXREG means transmit register. PIE is not required. TXSTA means transmit status register. SPBRG means serial port to baud rate generator. These are the registers. So next we will see the steps. These are the steps required for basic serial transmission. These many steps are required. So first step is that, so these are the steps, that is first set high speed transmission, then set baud rate to 9600 bits per second, set asynchronous transmission, enable transmission, configure this thing, wait until USART is ready, transmit a character. All these are the steps, we will see one by one. So this is the first step. First step is that we need to set high speed transmission. Basically there are two types of transmission, high speed and low speed. Here we will be using high speed transmission. So how we will set this high speed transmission? For that we are having a particular bit. That bit name is BRGH. BRGH means baud rate generator high. Baud rate generator high. That is BRGH. So if you are making BRGH equal to 1, here you can see, if you are making in the asynchronous mode, here there are two types of transmission, synchronous and asynchronous. USART means universal synchronous asynchronous receiver transmitter. But usually we will be doing only asynchronous transmission. Why? Now we are dealing with only asynchronous transmission. Usually it is like that. Why? If you want to have synchronous transmission, one more line should be there, clock. Synchronous means it should be something synchronous with some clock source. So one more line is required. For that we are omitting that, and we are doing only asynchronous transmission. So in the case of asynchronous transmission, BRGH equal to 1 means it is high speed, BRGH equal to 0 means it is low speed. And which is that bit? Bit number 2 of TXSTA register. This is the register. BRGH is the bit. That bit is present in register known as TXSTA, that is transmit status and control register, and its address is 98H, and BRGH is the second bit of, this is bit 0, bit 1, bit 2, second bit of TXSTA. So when you are writing the program, how we will write? We need to set this bit of this register. How we will write? BSF TXSTA comma bit number 2, TXSTA comma 2, or sometimes you may not be remembering this bit number. Then what you will do? You can give the name itself. BSF TXSTA comma BRGH. BSF TXSTA comma BRGH. That means BRGH bit in TXSTA will be set. So this is the first step. Second step is that we need to configure the baud rate. That is, we need to set the baud rate to 9600 bits per second. What is this baud rate? Baud rate means it is the number of bits per second, number of bits transmitted per second. That is the most important criteria when you are doing a serial transmission. How many bits are transmitted in 1 second? That is one of the important criteria. So that we need to set. And in the default case, it is 9600. And I need to set that. How I will set? For that, you are having a register known as SPBRG. In the slide which I had shown before, BRGH was a bit, but here SPBRG is a register itself, 8-bit register. And when I am writing a particular 8-bit value into this register, a particular baud rate will be set. For example, I am writing one value 10, hexadecimal 10 into SPBRG, then some baud rate will be set. So how we will find which value is to be written for 9600? We need to find what value is to be written for getting 9600 as BPS. So for that we are having equation. So this is the table showing that equation. So for BRGH0 there is set of equation, BRGH1 there is one equation. So here we will be using only this equation because we had configured BRGH as 1. So what is the equation? Baud rate equal to F oscillator by 16 into x plus 1. So what is baud rate? Baud rate you need to get, that is 9600. What is F oscillator? F oscillator means your crystal oscillator frequency, not the CPU frequency, crystal oscillator frequency. So it will be, here you are using 4 megahertz. So baud rate will be 9600. F oscillator will be 4 megahertz. So when you are substituting these two, you will get the value of x. This x is the value that is to be given to SPBRG. And since SPBRG is an 8-bit register, you can give only values from 0 to 255. SPBRG is a register. So when you are substituting 9600 and 4 megahertz, you will get x as 25, decimal 25, you will get the value. So that is, this 25 is the value that is to be written into SPBRG for getting baud rate 9600. So when you are writing decimal 25 into this register, it means your baud rate has been set to 9600. So that was the second step. So now baud rate is set, high speed transmission is set. Third step is, so there is one more problem. So for example, I need to have I need to change this what will say, baud rate. I need to change it to some 2400. Then what you will do? Again you need to substitute in this equation and you need to find the value. Again you need to do the calculation. But actually that is not required. It is given, most of the baud rate is given in the data sheet itself. So these are the tables showing that. So there will be two set of tables. First set it will be written baud rates for asynchronous mode BRGH0. Second table will be baud rate for asynchronous mode BRGH1. So you should take this table. So in the data sheet you will be having so many tables like this, and these two tables are different. Why? Here you are using F oscillator 20 megahertz, here you are using F oscillator 4 megahertz. So which table you should take? You should refer this table. So you can see this is the baud rate in kilobaud. So this is your 9600 bits per second. So if you are seeing what is the value that is to be moved to SPBRG, that is 25. From this table you can find. So sometimes I need to change the baud rate to 2400. So what you will do? 2.4, it is 103. So from this table you can find the baud rate directly, or the decimal value that has to be passed to SPBRG. All these are decimal values, not hexadecimal. So now you had set your baud rate. Third step is you need to set the transmission as asynchronous. That is the third step, because we told there are two types of transmission, synchronous and asynchronous. So there we need to set this transmission as asynchronous. So how we will set? For that you are having a bit known as SYNC bit. SYNC, that is sync bit. Where is this bit present? This is present in bit number 4 of TXSTA. This one. So this bit is the present in bit number 4 of TXSTA. And if you are making this sync bit as 1, it will be synchronous. If it is 0, it will be asynchronous. So since we are doing asynchronous transmission, I am making SYNC as 0. Right? So now we had configured my transmission as asynchronous. That is the third step. Fourth one, we need to enable the transmission. So that is the fourth step. So now till now we had done our initial configuration. Now we need to enable the transmission module. So that will be done by TXEN. That is transmission enable bit. TXEN is also a bit present in TXSTA. That is bit number 5 of TXSTA. So if we are making that bit as 1, transmission will be enabled. If it is 0, transmission will be disabled. So here I am enabling, so TXEN equal to 1. So I had enabled the transmission. That was step number 4. Next step is we need to configure these two pins, because I told you are using pin number 25 and 26, and that is, it was written no, RC6 and RC7. You had seen here 25 and 26. 25 is transmit, 26 is receive. So before doing my transmission, I need to configure the functionality of this pin. It is in the default case, these two pins will be configured as digital IO, that is RC6 and RC7. I need to change that functionality from digital IO to USART pins. That is, I need to change the functionality of that digital IO to the pins of USART, so that it can't be used as digital IO. And after configuring this, it will be working as a pins of USART. So that functionality I am going to configure in the next step. So how will I configure that two pins as pins of USART? That is done by using this bit, that is serial port enable. That bit is present in register known as RCSTA, that is receive status and control register. This is another register, RCSTA. So bit number 7 of RCSTA is SPEN, that is serial port enabled. So here you can see, if you are making SPN equal to 1, serial port will be enabled, that is, it configures RC6 and RC7 pins as serial port pins. That is it, that pin functionality I am going to set it as USART. That is, from now onwards it will be working as pins of USART. So that is being done here in this step. Next step, what is the next step? So now we have done all your initial configuration. Next we are going to transmit. So this was a program for continuous transmission of a character A. This was I am showing you a steps for continuous transmission of A, for transmission of a single character. So now I had completed all my initial setting. Next I need to transmit a character. So I am going to transmit a character. Before transmitting a character, what should I do? I need to check whether USART is busy with transmitting some other data. Right. Sometimes USART may be sending some other data at this present moment of time. So before giving a data to a USART for transmission, I need to check whether it is busy or not. Busy means whether it is busy with some other transmission. So how will I check whether it is busy or not with some other transmission? For that we are having a flag, that is transmit interrupt flag, TXIF. This is that bit. TXIF is a flag. What is meant by flag? To show certain status. So this flag is showing the status of USART, that is whether it is transmitting some data or not. So if TXIF is 1, it means your USART transmit buffer is empty. What is meant by that? If USART transmit buffer is empty means now your USART is ready to transmit. So whenever that buffer is empty, I can give some data, so it will transmit. But whenever it is full, what is meant by that? It is having some data that is being transmitted. So if it is full, it means that it is having some data and some transmission is in progress. So wait until USART is ready to transmit. That is, wait until this transmit buffer is becoming empty. So how will wait? That you need to continuously check until TXIF is becoming 1. We need to wait until TXIF is becoming 1. So if it was in C, I will write like this, while TXIF equal to 0 semicolon. That means what? When this condition is true, it will execute here itself. When this condition is false, it will come down. So here when TXIF is 0, it will wait there. It will keep on continuously executing that. And when this is false, when it is becoming false, TXIF equal to 1, then it will come down and it will execute the rest. So when you need to wait until TXIF is becoming 1, that is USART transmit buffer is empty. So you need to wait until that. How we will write it in assembly? This was in C. I will write in assembly. I will write. You need to wait until that. So BTFSC or BTFSS, which one you should do? BTFS C or S? S. Why, if you are giving C, is there any problem? Is there any problem? Change the program. But if you are, let us take BTFSS. So BTFSS, which is the register, and this TXIF is present in a register known as PIR1. So BTFSS PIR1 comma TXIF. That way can you write? And what will be next statement? Go to L1. So what is happening? If that bit is set, your go to will be skipped, right? No? Like this. So PIR1 is the register, TXIF is the bit. First it is checking whether this bit is 1. If it is 1, what it will do? It will skip this statement. If it is 0, what it will do? It will execute this. Right, no? That is, if this condition is false, this statement will be executed. If it is false, TXIF will be 0. So when TXIF is 0, we need to wait here. So go to L1. Again it will wait. And when this is becoming 1, this statement will be skipped. So this is how you will be checking, or this is how you will be waiting somewhere by using this. This is the last step. So when it is ready, you can give your character to a register known as TXREG. So TXREG is a register which holds the character to be transmitted. So after checking or after finding your USART buffer is empty, you can give the character to TXREG. What is the character which is to be transmitted? Now I am going to transmit a character A. So if it was in C, I will write like this. That is, I need to transmit a character, that is A. So that A should be moved to TXREG. That should be the last statement. So if it was in assembly, how we will write? Assembly. Move LW. Yeah. Move LW ASCII value of A. So what is ASCII value of A? 0x. Then I will write like this. Right? Correct? Not correct. Not correct. So if you are putting A in single quotes, automatically ASCII character will be taken. If you are putting A in single quotes, automatically ASCII character of A will be taken to W. Then from W I am writing into TXREG. So write a program for continuous transmission of this character. So these are the steps. So wait a minute, I will some more I need to tell. So these are the steps for transmission. Next we need to see the step for reception. So what are the steps for reception? There is only very little changes. Registers are almost the same. Steps are also almost the same. There is some addition in this step. Here you can see CREN bit. That is additional. Similarly, instead of TXIF, you will be checking RCIF, and finally your received data will be present in RCREG. Right? So this is the step which has been changed. So in the first case you had only enabled the transmission. Now we need to enable reception also. So how we will do? For that you are having a bit known as CREN. CREN means continuous receive enable. So that is a bit in RCSTA. That is bit number 4. So in asynchronous mode, if you are making it 1, it enables continuous receive. That is continuous receive enable. I need to make that also as 1. All the other initial settings were the same. In addition to that, we need to write this also. Then next step, instead of TXIF, you are checking for RCIF. That is receive interrupt flag. So before taking the character and after receiving, your character will be present in which register? RCREG. This is the register which is holding the character which has been received. So when I am telling transmission of or reception, I am telling with respect to PIC. When I am telling steps for transmission means PIC is transmitting to something. Similarly, when I am telling reception means PIC is receiving. With respect to PIC only I am telling. So reception means when it is receiving some data, that data should be present in some register. No? Then only I can read that register. So that register is your RCREG. So before reading the data from RCREG, again you should check whether the reception has been complete or not. Because since you are doing serial transmission, bit will be transmitted one by one. So you need to check whether your reception is complete. If that reception is complete, then only you need to read from that register. So how we will check whether the reception is complete? That is done by using RCIF. And if RCIF equal to 1, it shows that USART receive buffer is full. So when the reception is complete, RCREG will be or receive buffer will be full or empty. when the reception is complete, whether this buffer will be full or empty. Empty. Full. If you are receiving something your plate, it will be full, no? So here, if the reception is complete, your receive buffer will be full. But in the case of transmission, if it is ready to be transmitted, that buffer should be empty. If it is empty, then only I can give some data. If it is full, then I cannot. If we are having a pot and if there is some water, it is completely filled, I cannot fill again. So that should be emptied, then only I can fill the same amount. So before transmission, you need to check whether that buffer is empty, that is TXIF equal to 1. If you are going to receive, that plate should be full. There also you are checking RCIF equal to 1. So if TXIF equal to 1 means your transmit buffer is empty. RCIF equal to 1 means your receive buffer is full. So here you need to wait until RCIF equal to 1. So that is the difference. Don't confuse between these two. Remember the example of one pot, completely filled, completely empty. So it will be easy for you to understand. Understood? No? Any doubts are there? So you need to check whether, or you need to wait until this RCIF is 1. After it has become 1, you can read the data from RCREG. How we will read the data from RCREG? I need to read the data from RCREG. So if it was in C, I will write like this. In assembly, how we will write? I need to read something from, I need to read from a file register. Which command you will use? I need to read the content of a file register. Which command you will use? There are three type of moves, no? Move LW, move WF, move F. So you will use move F. Move F is used for reading data from a file register and giving it to some destination. Destination can be either work register or your same register. So here what you should do? You need to read the data from RCREG, give it to work register. So move F, RCREG comma 0. Move F, RCREG comma 0. That means you are reading from RCREG, writing into work. Then you can also write something. For example, I had read the character A. How I will show that? I had read one character. I need to show that. No? So you can retransmit it back. For example, you are communicating between PIC and PC. PIC is receiving some data. I don't know which data is being received. So what you will do? PIC will receive that data, again retransmit it back. So in the PC you can see. So for serial communication, for doing the serial communication from PC, you are having a software known as hyperterminal. I will show how to do. Now let us hear. Here I am having a hyperterminal, and here you can give some name. COM port, all these things I can give, and after that you will be having a window like this. Here if you are typing something through your keyboard, after getting this, if you are typing something through the keyboard, that character will be transmitted through that Db9 connector from PC. Simply if you are typing something here, that character will not be shown here, it will not be displayed. In the default case, characters that are transmitted will not be displayed here, but actually it is going out through the Db9 connector. So whenever you are typing something, it will not be displayed, but it is going out, that is, it is transmitting. So I need to know which character is being transmitted. So what I will do? PIC will receive that character, and after that what it should do? It should again transmit it back to a PC. So whichever character it is, being received, whichever character it is being received in that Db9 connector, it will be displayed here. For example, PIC is receiving I am pressing a character A in the keyboard. So PIC will receive that A and it will retransmit it back to PC. So here I can see A will be displayed. So now I am telling you to write a program for continuous transmission of A. So how we will see this A has been transmitted or not? Here continuously you need to get A. A will be continuously displayed here. That is, which character your PC is receiving, that will be shown here. Which character it is transmitting, that will not be shown. So if any character is being received by the Db9 connector of your laptop or your PC, that will be shown here. But in the laptop there is no Db9 connector, is not there. So there you need to use something known as USB to serial converter. One cable is there, USB to serial converter. That cable you should use. In the desktop you can test this. So when you are doing at the time of simulation, we need to get complete A's here. It will be filled with A. So write a program for continuous transmission of a character A. So follow this step as it is. Go to loop at last. Rest all the steps are same. And how we will move this decimal 25 using your move LW? How we will move this decimal 25? Either you can write like this, (0D25) or like this, dot 25, dot 25. So you can see like this. So here you can see, first I had set BRGH, then 25 has been moved to SPBRG, SYNC I had cleared, TXCN it was enabled, SPN also enabled. Then in the main loop I am testing BTFSS PIR1, TXIF, go to loop. Bank cell TXREG, move LWA, move WF TXREG, go to loop. So continuously it will be transmitting this character. So after finishing, you need to simulate the virtual hyperterminal. In the Windows we had seen one software known as hyperterminal. So we need to simulate that. So for that you can click on this virtual instruments mode. Here you can see virtual instruments mode. One CRO icon is there. One here you can see, no? One icon is there, virtual instruments mode. So when you are clicking on that, you can see all the virtual instruments. So from there you take virtual terminal. From there you take virtual terminal. That is the simulator for hyperterminal. Take virtual terminal and place it here. So this is your virtual terminal. This is the RX, TX, ground is not required. Here, since it is a complete circuit, ground and power it is not required now. So only RX and TX you need to connect. So how we will connect? From the TX of PIC, that is pin number 25. 25 is TX of PIC. From there I need to connect it to RX of the virtual terminal. Similarly, from TX of virtual terminal to RX of PIC. Any doubt in this connection? From TX to RX of virtual terminal. Here virtual terminal is acting as your PC. So from the TX of PIC you are connecting to RX of your PC. Similarly, RX of PIC you are connecting to TX of PC. Here there is no need of that level converter and all. We are going to simulate only. So no need of level conversion. When you are actually doing the hardware, we need to have that level converter. But here it is not required. You can directly connect it. So only this much is your connection. And if you are giving run, you can see all these things. And when you are stopping the simulation, don't close this window. When you are stopping the simulation, don't close this window. You can directly stop the simulation. Then automatically that window will be gone. Don't close that window. You can run as well as stop from this bottom portion. And by mistake, if you have closed this, you can take it from debug. If you are getting any other character other than that you had given, sometimes you may have given A and you will be getting some other character. In that case, your baud rate is wrong. That means you had given 4 MHz in the crystal frequency you will be giving. No? Sometimes it may be 1 MHz. So here we have done the calculation with the 4 MHz crystal. So in the inside PIC you should give processor clock frequency as 4 MHz. If you are changing it into 1 MHz, you will be getting X. Some other value you will get. So it should be 4.